Hey there, my name is Zizhen. In this video, I will do a comparison of the learning models on two-sided bandits. The multi-arm bandit is a famous machine learning problem. There is a single player and multiple slot machines. The goal of this player is to find an arm with the highest chance of paying off. A more complex version of this problem is then the two-sided bandit problem. There are multiple players playing at the same time. Players have preference over the arms and vice versa. When two or more players put the same arm, a conflict arises. Only the most preferred player in this particular arm is able to pull the arm. The winner's reward isn't affected by the rank of the arm. The goal is to find a stable matching such that it maximizes the total reward. There are three popular algorithms for solving this single-player bandit: AlphaGreedy, Thompson, and UCB1. The motivation of my project is to find out how do they perform for solving the two-sided version. First, let's define our model. We have N players and L arms. Each player and arm has a strict, fixed rank over the opposing side. For example, player 1 prefers arm 1 the most, and arm 1 preferred player 2 most. Notice that we do not allow indifference. At time t, each player attempts to pull an arm. Each arm then picks the winner from the candidates according to its rank list. The winner gets a reward that is equal to 1 over the rank of the arm. For example, with a rank list of P1 above, if P1 successfully put arm 2, he or she gets a reward of 1/2. Here are some current knowledge. For AlphaGreedy, it was reported that with global ranking on both sides, probability of getting a stable matching increases as alpha increases. When alpha is 0.9, the probability is very close to 1.0. Note here, global ranking on both sides means every player has the identical rank list over the arms, and vice versa. An adapted version of UCB1 was proposed in 2020. With probability lambda, we pull the same arm as the last round. Otherwise, choose the one with the highest UCB value from the plausible list. An important assumption of the CAUCB algorithm is that it requires information sharing among players. Lastly, for Thompson, I made a simple change. Choose the arm with the highest utility, which is reward multiplied the beta distribution. The evaluation involves two aspects: probability of convergence to stability and time on convergence. The variables are whether the players or arms are globally ranked and number of arms. And then here are some parameter settings. Okay, this bar graph shows the probability of convergence with respect to global or arbitrary rank. It shows that Thompson is very reliable for all cases, followed by Greedy algorithm, which performed well except for the arbitrary rank on both sides, with a probability of 0.89 to stability matching. For CAUCB, it performed well in case of global ranked players, arbitrary ranked arms, and performed worse in arbitrary on both sides with a probability of 0.86. So now let's fix the setting to arbitrary on both sides. As we increase the number of arms from 5 to 10, all algorithms performed better, with a probability rounded to 1.0. Worth noting that CAUCB improved about 12% in terms of reliability. Either global or arbitrary rank, Thompson converges to optimal matching really quick. CAUCB can generally find a solution close to the optimal matching fast, but takes a long time to settle down its noise. And lastly, Greedy converges around 5,000 steps for global on both sides, and converges slower as we introduce arbitrary ranks. Last but not least, as we increase the number of arms, both Greedy and CAUCB converges faster to the optimal solution. In summary, Thompson performed the best in terms of probability of stable matching and time of convergence. Greedy performed better than CAUCB for reliability, and CAUCB performed better than Greedy for time of convergence. Thank you.